Let us start the lecture 5 of module 2. In this lecture, I will continue the analysis of the converter circuit, and we are discussing about the 6-pulse converter circuit, and that is a bridge rectifier. Last turn we saw this in the rectification mode. We saw the various voltages, including the DC voltage, and also we saw the valve voltage, and we also found this currents in the various valves as well as the phases current, and of course the DC current we have assumed that this is a constant. To know the inverter operation, again the circuit which I have shown here, this is 6-pulse bridge rectifier circuit with the numbering of the valves 1, 3, 5 and 4, 6, 2. We have the two groups. Now in the inverter operation, what we do, we have to delay the firing angle. As I said, the commutation voltage of a valve 3, it is your EBA. This is a commutation voltage of the valve 3. Here the valve 3 means this valve will be fired if the gate pulse is available. From here, this is your alpha is 0, and we can go up to here alpha is 180 degree. In the rectification mode, if your alpha is still here 90 degree, you are getting the 0 voltage. At 90 it is 0, but just before here you are getting the positive output across this converter circuit, and once your alpha is more than 90, the voltage is going to be reverse, that is negative, and we can fire in this duration because the voltage across valve will be positive, and then we can give the gate pulse and the 3 will be fired. So this is your commutation voltage of the valve 3. In the inverter operation, means our alpha is delayed, means alpha is greater than pi by 2 or 90 degree. In ideal case, if alpha is 180 degree, means we are firing here, although there is some minimum angle required that we cannot fire between this period. Normally this is the safer portion and we should avoid, we will see later on. This is called the extinction angle or the commutation margin angle. But for ideal case, let us say the alpha is delayed up to 180 degree, then we can get this following voltage. Here you can see the valve numbers are in this figure. It is given, that is the valve 4, 6, 2 and 4, means they are conducting during that period. The first here, the portion, it is showing the voltage at your first terminal. This is terminal here, I can say. This is a terminal 1 line link. Here is 1, here is 2. I can say top and bottom. So the upper portion shows that your top voltage, and below one this one, and your output voltage will be the first. I can say the voltage this minus this will be the instantaneous voltage across the link. Now you can also see if valve 4 is conducting, what will be the output voltage at that limb. 4 is coming, means here it is your nothing but it is your EA, because 4 is connected to phase A. So here if this is conducting, means voltage here will be appearing your phase A voltage, and similarly if 6 is conducting, then EB, 2 is conducting, then EC. Similarly here is 1 is conducting, then EA at this one, 3 is conducting, then EB will appearing, and so on and so forth. So if valve numbers are written to you, then you can write what will be the voltages, that is the phase voltages that is appearing on the upper as well as the lower limbs. So here that 6 it is your EB, here 2 is EC also, yeah. Similarly you can see 1 is your here EA, 3 is your EB and 5 your EC. And the voltage, the final, the top voltage minus below voltage will be your output voltage. Now from this phasor, whatever here is shown, if you are going to subtract this minus this, you are going to get this voltage. And this is, you can see, this is your axis. Here we are getting the line to line voltage, that is the 6 pulses are coming in one cycle, and this is the negative voltage. Means this terminal becomes negative, this terminal becomes positive, and so on. So this is a concept of the negative. And if you see the valve voltage here, now it is coming this one. When it is conducting, it will be 0, and most of the time here it is a positive. Here alpha is assumed as 180 degree. Mind it. If alpha is less than 180 degree, we will have the different shape, and that we can see in the next figure. Here let us draw the what will be the output voltage in the case of inversion, means your alpha is, let's suppose take alpha is 150 degree. In the previous case, it was your alpha was 180. It was just equivalent to a rectifier circuit. The voltage magnitude will be the same when alpha was 0, only the polarity is different. So now I am going to take, if alpha is 150 degree, means where you are, just you have to draw what will be the output voltage across this, and we also will find what will the voltage across any of the valve on the same figure. Again here in this is the top figure that's showing it is a line to line voltage, and the below one can be taken as the phase voltages. So I can start here is writing, it is nothing is given, I can write EBA, and this EBA is a the commutation voltage of valve 3. So we can fire our valve any period from here to at this point we can. So as I said here, this EBA is the valve 3 commutation voltage, and we can fire here from this up to here when it is your EBA is positive, means alpha here is your 0, here alpha is 180 degree. Now I said I want to draw the output DC voltage. Let us first draw, and for knowing this output voltage we have to know the various line voltages, and already I have marked EBA, then we have to mark other line to line voltage very clearly, then we will get the output voltage. So this is EBA, then 120 degree will be displaced, that is your ECB here, this voltage, and then another will be your EAC, this is your CB. So we have marked 3 voltages because you have to again go for the cyclic one. So EBA you have marked, so B becomes C and A becomes your B, and here EAC, and similarly we can write this. Now you can see this is your this voltage EAC, here it is nothing but ECA. Just you can see from here, this is a reversal of this voltage on top, and similarly we can write here this will be your EAB. Before that we can write this voltage is the reversal of EBC. So these are the line voltage. How I wrote here from very well, I just defined first one EBA, and then you can see this is 180 degree. Now another 120 degree, this is a 60 and 60, so that will be starting here. It will be your B becomes C and A becomes B, so I have written ECB. From this cycle you can see again 20 degree here. Now it is your C becomes A and B becomes C, and this is that. Now for intermediate you can see this voltage is coming here, this is a reversal of this, so it is becomes CA rather than AC, because that's we have reversed the minus sign. Similarly we wrote here the BC, it is a reverse of CB, and so on and so forth. So you have to mark very clearly line to line voltages, top as well as the bottom. Now as I said, I want to draw the output voltage corresponding to alpha is equal to 150 degree. Now you have to see where is the alpha. Alpha I start here omega t is equal to 0 at the beginning of this graph. So now this is a 180 degree, this whole cycle is this, so you are going to have here this is your alpha is 150 degree, because this portion here is 60 degree. You can see in this is 60, 60 and 60, so 180 degree. So this is your 60 degree and half of this is 30 degree. So 80 minus 30 is 150 degree, it will be lying here, and you will find this is a cross section here 30 degree. Now we have to, now we are just giving a firing pulse at this point here, your 3 is going to be fired. Once your 3 is going to be fired, now what will be the output voltage? You can see from here, as you know, this is 3 is fired. Now here we are getting EB, and before that 1 and 2 conducting. We are assuming this 1 and 2 are conducting and 3 is giving the pulse. So 2 were there, so here it is your EC was there. So the voltage here EB minus EC will appear. Now you can see where is the EBC is there in this graph. Now you can find this EBC here, it is starting at this point. This is EBC. You can see as I marked here also, this is a, once you are giving the pulse here, suddenly it follow the EBC, because this was the EBC. So this is starting from here, and now this will go up to 60 degree. Again after 60 degree your valve 4 will get the pulse, and once your valve 4 is getting pulse, means just you move here ahead, it will be, this is coming here, we'll see, and before that also we can plan, but right now let us see, we are going to give the 60 degree, here it is firing, means your 60 will arise here. because the 30 and 30 always, because here it is 30 degree, it is conducting, then next here 30 degree means 60. After all the valves are getting, as in beginning I assume that valves are getting the pulses after every 60 degree. So at this point your valve 4 will get pulse, and once valve 4 will be getting the pulse, here now you can see this is coming here, it is EA and this was your EB, means we are going to have EBA. So we have to find where is EBA, and then it will be suddenly follow, and you see where is EBA at this pulse. So EBA you can see here, it is at this point it was flowing here till, and then it is going to follow here EBA. This is your EBA, it is going to follow, you see EBA, and then it will again go here till again 60 degree here, where your valve 5 is fired, here valve 4 is fired. Just we are writing the valves where it is giving the gate pulses, because you can see the difference between here and here, it is 60 degree. So next 60 degree here, it is your, and it is a sequential firing, means 3, 4, 5, 6, 1, again it is a cyclic one. So it was here, it was coming here, then it was coming here, and now we have reached here. Now your valve 5 is getting pulse. Now valve 5 is getting pulse, what will be the output voltage? It will be ECA, and ECA you can see it is suddenly here, it will be jumping at this one, because this ECA is this one. So your output voltage, you will see it will be continuously, it will be like this, it will be going like this, and here again here this is. You can also complete for one cycle, you can go before as well here, and we will find this is your it was going like this and like this. So it was 3, 2 and 1. You can also verify that this will be the output voltage, because 3 again 1, 2, 3, 4, 5, 6, 1, 2, again it is going to be in cyclic order. So this is your output DC voltage which is appearing across this in case of inverter mode, and we have taken alpha is equal to 150 degree. If alpha is not 150 degree, it is 180 degree, this firing will start at this point here, and then it will go. This will be actually, this line is this shifting like this, but it will be coming here at this section, and then we are having this pulse, all the pulses will give in. Now this is your output voltage that is appearing across your this link, and this is, you can see this is always the average here. If you will calculate, it will be your the DC, and also you can verify by your output voltage equation. You can just simply the VD, this we find it is your VDO cos alpha. Put alpha is equal to 150 degree, it will be negative, and some the value will be appearing. Now the main important here, although this is a very simple case where we are assuming the overlap angle is 0, means commutation from one valve to another valve is a sudden instantaneous, because when you are getting the pulse, 3 is taking complete current from here and the sudden switch is there. But it is not true, and we will see in the next cases for when the various modes of operation will be there. Now I want to draw the valve any voltage. Here let us suppose I want to draw the valve 3 voltage, again on the same plane. Here I will also draw here, because the voltage will come on that, so it will be clearly visual. Now you can see once valve 3 is fired, we can start from here. The voltage across this will be 0, and it is continuing up to here, because each valve is conducting for 120 degree. So the voltage across here, actually here it's no color, so but we can write here, this is a volt, here we are coming up to this one. So this is valve 3 is conducting during this period, so the voltage will be 0. Now after that 3 is off and 5th is taking care. Now you can see if the 5th is taking care here, so voltage across this is coming your EC, and this will be EB always. So the voltage across this will be EBC, and once 5th is going to be fired or is fired, then the voltage across this will be EBC, and you have to see where the EBC. EBC you can see this is your EBC is coming all the way here, this is going here, and suddenly it is coming here EBC, and it is following this. because this is your EBC, this portion it is EBC. You see this is EBC is coming, so it is going here and it will continue. Let us see once your 6 is here getting pulse. Once 6 is getting pulse, there will be no change, it will follow the same, because here the 6 is pulse, still the 5th is conducting. So what will happen here, it will follow till even though 6 is fired here and it will continue. Here the change of the valve voltage will only occur if there will be any conduction here in the upper limb. If you are talking about this, so if this is conducting or this is conducting, then it is going to change. Changing here will not change here, because that at that time it was the same valve was conducting. So it will follow even though up to the 6th valve firing, it is going to be your this one, and it will be going up to here. This is 6 is fired and still it will continue, and here 1 is going to be fired. So it will be going up to this portion here. This is your valve voltage I am drawing, the thicker line. Now 1 is fired. Then A is coming on the cathode of 3 valve and B is also there. So the voltage across 3 is EBA, because B is here and A is coming here. So this is EB minus EA voltage, always we are drawing the direction. So EBA, and now you have to see where is the EBA. You can see EBA is this one, this is your EBA, and it will follow here and then it will continue. So here 1 is fired, then even though 2 is fired, it will won't affect its voltage because it will continue and it will go till 3 is fired. Once 3 is fired, means it will be automatically it is 0. Now come back this side, because we have to draw the complete cycle. So it is not completed, then we can come another side here and we have to complete this. Means when the 3 was fired, before that your valve 1 and 2 were conducting. So 1 and 2 were conducting, it means the voltage across 3 is again EBA, because 1 is conducting, 1 is coming, EA is coming on top, and here EB, so EB minus EBA, and now you can see what is the EBA. So your EBA here, before that it was conducting, this is your EBA and it was following. So it was here, even though it was following till your this complete, it was here and it was EBC here. You see, because 1 was fired here, 2 firing will not affect anything because the voltage will be same. Now EBC you can see from start from here, just you can see we have started here. So it is a complete cycle. So the valve voltage you can see here, it was coming here, EBC here, again the cycle is completed. So EBC you can see suddenly here, now EBA is following, EBA following. Once 3 is getting pulse, suddenly it is 0 and then it is continuing, and this is your voltage. So this is valve 1 voltage. Similarly you can valve 3 voltage. Similarly you can draw the voltages of any of the valve. You can see here in the valve voltage, in this case this valve is experiencing the voltage positive all the time except during this period. So this is a negative voltage appearing across the valve 3. This is conducting, it's no matter, but in the remaining period it is positive. And that's why in inverter operation this is a big deal, because whenever there is any spurious signal, the valve may conduct. Even though you can say there is a huge dV by dt is there. There may be also there is certain jumps in the voltage, certain jumps in the current that may lead to misfiring of this valve, and that is called commutation failure, or there is something other problems. So that's why inverter operation is very risky and is very cautiously maintained. So anyway, we'll see other effects and mal-operation of converter circuits later on, but here again this voltage wave shape of inverter and the converter I'll be using, and then we'll see what is the various possibility of the mal-operation of the converter circuit. So this is your DC output. The ideal when there's no overlap angle, this U is 0, the DC output in inverter operation when the alpha is more than 90 degree and less than 180 degree, and the valve voltage for 3 we draw it here. Now let us go for now the realistic case for overlap. This was the ideal case which is not existing. very rarely, but now we have to go for when there is some overlap angle. Again, I remind you, this overlap angle is the angle when the two valves in the same limb, same upper or lower, they are taking time of the current change from one valve to another valve. So that's why it is written here, the shift of current from one conducting valve to another conducting valve is not certain due to the certain problems like leakage, more leakage inductance of the converter transformer, and sometimes your supply system, weak supply system, may also leads due to some other problem. So the duration when the current is shared by the two conducting valves is called the overlap angle U, and it is known as the commutation angle. To show it commutation here, again this was the case. Now I can say here we are having this two lines, upper, I can say upper limb valves, lower limb valves. Here I can say 1, here it was your 3, here it was your 5, and again it was 1 or so on. And the conduction of each here, it was your 120 degree. This 120 degree here means each valve in the upper limb it is conducting for 120 degree. However, the pairs were conducting for the 60 degree. Now here I can say this is half, this is half, this is your 2, here it is your 4, here it is 6, and again here is a 6, and so on and so forth. So this was the ideal case. You can see here your 6 1 was conducting, then 1 2 was conducting. Here you can say, you see this 3 and 2 in this zone, so 2 3, here 3 and 4, and 4 5, and again 5 6, and then we have again reached the same here. So this was the 2 valve conduction case when U was 0. But when U is not 0, then what will happen? There is some period when the two valves will be conducting together, and this depends how long they will be conducting. There is a possibility this U will be less. U will be, again, U can vary from your 0, means it can be 0, and it can be more than your 120 degree even. But we are not going for this U20 degree is unrealistic case, but normally it is very much possible that U can be more than 60 degree. Now let us see if our U is less than 60 degree. Again we can have the different cases, and thereby if we can have the different modes of operation, and that's I can say mode 1 is the case when your U is less than 60 degree. Means we can see from here, again I will come back to this one here. I can say the mode 1 operation when the possibility of the sometimes 2 valves, sometimes 3 valves will be conducting, and this is the case when U is less than 60 degree. There is a possibility, this is the case mode 2 is between mode 3 and mode 1, because this is more than 60 degree, it is less than 60 degree. So mode 2 is the case when U is equal to 60 degree. Once here it is a 60 degree, at all the time 3 valves are conducting, and the 2 from one limb and 1 from the another one, always maybe 2 from lower, 1 from here, or here 2 from here and 1 from here. So all the time in this mode 2 the 3 valves will be conducting. Now once here U is more than 60 degree, so the conduction becomes the 3 valves and the 4 valves. Means the minimum valve will be conducting 2 and 1 here, and but there is a possibility the 4 valve conduction 2 from here, 2 from here. It is not the 3 here and 1 here. It will be 2 here and the 2 here, that will be 4 valve conduction. So we are getting here the 4 valve conduction, and we'll see there's the period of 4 valve duration as well as the 3 valve duration that depends upon, and that can be very easily identified from this diagram. No doubt this is a very common that happens, because the U is not 0, always it will take time, because the current from one valve to another valve will take some time, it is not instantaneous. So this mode 1 is very common, but these mode 2 and mode 3 are not so common, but they may happen when there is some fault, some problem in the AC system, that we can land up in this condition when the 2 and 3 valves or 3 valves are conducting. So what we have to also analyze this case, and what will be the problems in during this, we'll see the harmonic component etc. will be tremendously high, the jumps in the voltages of the valves will be very high, and we'll also see this case as well. And first we have to take the case 1 here. Now to see this what will be the pattern of the conduction in the mode 1 here, mode 2 and mode 3, let us again draw this a bigger picture here, and then it will be more clear. Here I can say here your valve 1, here valve 3, here your valve 5, and then we are again going for 1 and so on and so forth. Now in the lower here, this will be, I can draw another line, this is your 2, here it will be 4, here it will be your 6, and again here your will be 6. Now to 2 valves conduction, here the ideal case already I have drawn here. Now let us see once we are going for the u is less than 60. Now what will be the 60? You can see in this duration, this valve here it is a 60 period. This is one is conducting for 120 degree, and u and this is your 60 degree. This is 120, this is 60, this is 60. Now we are assuming that this valve here, you can see from this graph also here. Now we are assuming that this is going to here, this slightly we are changing. It's not 60 degree, it is less than 60 degree. There is some period it is a delayed, means is going to off here this valve, it is taking some degree here, that is overlap degree, and this from here I can say this is your angle u. So the remaining period here, this portion here will be your 60 minus u. This here will be 60 minus u. So similarly all the valves, we are again assuming the symmetrical, because the commutation, that is u is the same for all the valves which is taking place. It is not the u is changing. It is assumed that u is fixed due to the certain circuit condition, and it is same for all the case. So what will happen? This will be also going here. I can just make it here, and this will be here, this will be here, this will be here, and this will be here. Now to know the what will be the conduction pattern and how it will be conducting, let us start with this one. At this point we can draw the line. You can see in this period, one is there, one is conducting from here to here, this one is this portion. So if we start here, means one is there, so I can write 1, then your 6 is there, so I can write here 6 1 is conducting, no 2, because 6 1 is here, 6 is conducting this portion. In this zone you can see here, this is a 1 is there, because 1 is conducting during this here, so 1 is there, and here you can say 6 is there, so 6 1 is conducting. Before that you can see here, what was this one? It was your 5. So your 5 is conducting up to here, means I can write the 5, then 6, and then 1. So this was conducting here up to this portion. Now here in this case, now 1, 2 and 6, because 2 is also conducting this period here up to this portion. In this period, this is your 1, this is your 2, and this is the 6 also conducting, because here I shifted here, so it is 6 1 2. So this is also a symmetric conduction. It is not that abrupt. You can say here 5 6 1 goes off, because 1 is taking completely, commutation is over between 1 and 5. So 6 1 is conducting. Now again, now we are giving the pulse to 2. So this commutation between 6 and 2 is taking place for your u degree, and then your 6 will off, and then finally you can see here it is your 1 and 2 are conducting. Similarly, you can see here it is your 1, 2 and 3, because the commutation between 1 and 3 is taking place. So here the 3 is getting the pulse and 1 and 2 are basically commutating. So again you will find 2 3, and again I can keep on writing here 2 3 4, and here 3 4, here 3 4 5, and so on and so forth. We are, you can say, we are getting here 5 4 5 6, and so on and so forth. So again we are getting the cyclic, means here 5 6 will be remaining, and then we are coming here again. So this is the case of the 2-3 valve conduction, means U period here the 3 valves are conducting, and your remaining period, that is 60 minus U, is your that valve is conducting, that is the 2 valves are conducting. So this is the case of mode 1, and here also it is just, it is known to you, it is given here. Now we have to see if it is U is your more than 60 degree. Means what does it mean? Means the once this is more than that, now I have to remove here, and let us draw the more commutation here, and I can say this degree is going to be increased from here. This is 60 degree. Now I am drawing here, it is more than that, because it is a more than 60. This U is here, it is less than 60. If it is coming here, it is a 60. If it is more than that, it is more than 60. So I am skipping mode 2, because mode 2 is a special case, because if it is less than here, we will here, and always will find the 3 valves are conducting. So similarly we have to change this one also. This will be your, this is more than this 60 degree, because this is 60, here it is slightly more, and this is also here it is 60, so it will be here. So it is your 1, it is a 5 1 3, and now it is your 5. Now the lower portion also it will be changed, and here it will be your this, your this, your this, and here it will be this. So this will be removed, this red lines here, these red lines will be not there, and now we have to draw this, what will be the various conduction patterns and the angles for those periods. In this case we are now going to talk U is greater than 60. Now we can take any portion here at this point here. Now you can see at this portion, between this, your this 5th 1 6, and this was 4. So we are getting 4 5 6 and 1 are conducting. See it, this was your 4 4 6 2, like this 4 6 2 4 6, and again it is cyclic. Here it is a 5 1 3 5 1 again. So starting from here, you see in this period, this portion and this portion, because this is a period when it is starting. So this is here, you can say 5, here it is 1, here it is 6, here it is 4. So 4 valves are conducting during this period. Now I want to know what will be this degree when 4 valves will be conducting. You see, this was your, this is your U. Let us come further, then it will be more clear what will be this degree. Now in this period here, your 5 1 and 6. So we are having 5 6 and 1. No doubt this total period here is 60 degree. This period here is 60 degree. This is another 60 degree. Now I am going to write here again, from here to here. Now you will find your 5, this is 1 right here, no problem, 2 here, 6. So I can write here 6 and 1 2. So it is 4 valve conduction. So, this sequence will follow. You can see this is also symmetrical 4, 5, 6, 4 will go, 5, 6 will retain here, then again the 2 is fired, then 5, 6, 1, 2, 5 will go, then we will find here 6, 1, 2 and so on so forth. I can write here 6, 1, 2, 3 here, and then we can go for 1, 2, 3 and so on so forth. So, this will be conduction pattern. Now, we have to see how much who is conducting. You see which period, this period is your U, means this period complete, this is your U, because U is this period. Now, as per now definition, this is was for old case. So, this is your, I can say, U. Okay. Now, what will be this period? This is 60. So, this period will be your U minus 60. So, you can see that this period, when the 4 valves are conducting, it is your U minus 60. Means when 4 are conducting, always when 4 are conducting, it is U minus 60 degree. Now, I want to know what will be this your 3 valve conduction period. 120 minus U, because the total is 120. This is your, already we have gone for this 60, this 60 minus this 60. So, it is 120 minus U, means this is 60 minus U minus 60, here means it is 120 minus U. So, in the 3-4 valve conduction mode, your this period is your 120 minus U, and this period here, this period is your U minus 60 degrees, and the pattern will follow, and this is symmetrical component 3, then 4, then 3, then 4, then 3 and so on so forth. So, this is your mode 2 case, which is just going to happen. Okay. Now, let us go for analysis when the valve 2 and valve 3s are conducting, means now mode 1 where we are taking either 2 valves are conducting or 3 valves are conducting for the again the repeated manner. So, this figure shows that valve 1, 2 and 3 are conducting. You can see the 1, 3 and the here it is a 2 are conducting, means before your 1 and 2 were conducting, and 3 got the pulse and it is now fired, and but however, the current shift from 1 to 3 is taking some time, and that is U degree, and we are believing that this U degree is less than 60 degree. So, in this case we are going to have our, as I said, the conduction pattern here 1 and 2 are there, then 1, 2 and 3, because here 3 got the pulse, and it is now the commutation between 1 and 3 is taking place, means current which ID here, the current here in the you can say I1 was your ID and your I2 was your minus ID during this period. Once here 3 is fired, so in this period what happens, the current here I can say I1 plus I3 is going to be ID, because this current is going to decrease and this current is going to increase, and the finally here once we are having 2, 3, this is over. At this period it is your I3 is ID only, because 1 is off. So, in this period when the 3 valves are conducting, the current I1 and I3, because current shift from here, which was earlier at this point it was ID, now it is going to be 0 here, means I1, and I3 which was 0 here, now it is going to take complete current of the DC link, that is ID. So, that is why in between this period it is always I1 plus I3 is equal to your ID, because we assume the DC current is the constant in this link. Now, so this is the case when this valve 3, before that here 1 and 2 were conducting and 3 got the pulse and it is now conducting. Once it is conducting at that instant, now this will be the equivalent circuit of this here, because 1, 3 in the upper and the 2 were in the lower. You can see, just you can visualize, remove the other parts, you will find the same. Means simply here what I can do, here I can remove, this is the 5th link here, and this is your 2 are conducting. So, I can remove this is, and you can see we are finding this one. So, this is yours here, and now this is the circuit we are having here, you can see, because this is your ID which is flowing, and here it is your ID is flowing here. Basically, this ID here, it is a positive, not I1, because the direction here we are taking from positive to, but the phase here it will be negative. So, this is there. Now, the first point, once these two are conducting, what will be the voltage at this point? Means I want to know what will be the voltage here, that I can say VA. Because once your A and B phases are, now you can say it is a line to line fault. This phase A is short circuited with the B phase. Then what will the voltage here? That voltage, I can say this voltage will be nothing, it will be the average voltage of this. Now, the question arises why. Let us see any voltage VA here, and I am going to prove this VA will be nothing but it will be the average of these two voltages. Because there is some inductances here, I can write here, let us suppose voltage A here. So, this voltage I can write the VA means EA minus L di 1 over dt is your, let us suppose it is a VA. I can write the current which is flowing here I1, that is with this voltage minus the inductance drop L di 1, because I1 is flowing here, that voltage will be here. Similarly, I can write for this circuit as well, means here I can write EB minus L di3 by dt will be your VA. We are assuming the L is constant in all these three. Again, this is assumption, but L, that's the inductance offered by this transformer, is the same in all these three phases. Now, simply add it. If you are adding here these two, you are getting your EA plus EB minus L di 1 over dt minus, or I can say this is plus di3 over dt is equal to twice VA. Simply I add these two equations and I got it this. We know this in this condition, this I1 plus I3 is your ID, the DC current, and it is assumed that DC current is constant, and once you are going to derivate it, it will be 0. Means simply you can derivate it here, you are going to get di1 over dt plus di3 over dt will be equal to 0, because the DC current is a DC, and if you are differentiating with the time, it will be 0. So, what happens? This is 0. Now, you can say here VA will be your EA plus EB by 2 all the time. And this value is nothing but, again we are assuming these three phases are the balance, as again our assumptions are there. And then here I can write it is nothing but minus EC by 2, because we know we write here EA plus EB plus EC is equal to 0. So, from this equation we can write the EA plus EB is equal to minus C EC, and this is the case. So, this voltage is known to you, and then here it is conducting. So, this voltage is minus EC by 2, this voltage is EC. So, the voltage during this 2-3 valve conduction is your minus this minus EC. Yeah, this will be 3 by 2. So, we have to write this various the voltage equation, and now let us see here. So, VDC here across this link here, this is a small VDC, means it is having the, again this is your 60 degree, this is your 60 degree, and then we can, once we are starting from here. So, this is the total here, the complete, as I said, this is your U period, this is your 60 minus U period, means the total is 60 period, and again this pulse are symmetric and the repetitive. So, we can just write here what will be the VDC for this period only. So, I can write here the VD will be the two cases when the 3 valves are conducting, it was your nothing but EB EA plus EB by 2 minus EC, or it is nothing but minus 3 by 2 EC, because this value here it is nothing but minus EC by 2, so it is minus 3 EC by, and that is for U period, means here it is 0 to your omega t2 U period, means the 3 valves are conducting. If you are taking here instant is a 0 and then we are moving, means here it is a 0, then up to U degree this was the voltage. Then after here, once this is off, it is again following at normal one, means here this is off, now voltage here it is coming, means I can say now this is the commutation is over. So your voltage is coming here EB, and here it is your EC, means EB minus EC, and as usual it was coming your EBC, and this is your from starting from U omega t to here 60 minus U period. So, okay. So this is the voltage that we have written. Now to take the average voltage, as I said, this is for this period. Symmetrically we are getting for the another period, and here again 60 degree. So our average voltage we can write as usual that for only our pi by 3 degree period, and that will be giving your output voltage. So I can write here this Vd, the DC is 1 over here pi by 3. This is a for here I have written 1 over pi by 3, means 3 upon pi, and then here we are integrating from this complete period. This is in square bracket here. This is from U 0 to U. This is your minus 3 by 2 EC d omega t plus here U to what we are going to get 60 minus U E BC d omega t. One thing here we are starting, that's once 3 is taking place, at this point we are believing that there is no delay, means U is equal to 0. But here as a commutation voltage, once it is starting, as I said, whatever the voltage here EBA is the valve 3, you can start here or you can start something, some alpha degree delay. So once you are delaying here, then your 3 is once fired, then it is going up to the 2 period, that is your U period here, the commutation will occur, and for the remaining period the U will be over. So here instead of 0, I can start with the alpha degree, and then it will be here alpha will be added, here it will be alpha added, here it will be alpha added. We will see again when we draw the voltages. So this is your average, even though you can see from this diagram, see here, this is the same case. You can see once your this valve is fired here, then your this period will be U, but we are delaying it, means once it is delayed here, your EA is continue to conduct, means your 1 is continue to conduct here. Now once 3 we get the pulse here at this point after alpha degree delay. Now in this period U, your you can see this is coming your upper limb valve, it is a minus EC by 2 is coming here. Lower here it is EC is continuing. So in this period here U, it is this minus this is the voltage, and for the remaining period here this EB minus EC is appearing, and this is again the repeated one. So here if you are starting from here, then you have to take the here phasors accordingly, but we took EBA as our reference mandate. So EBA reference was 0 here, because for I said this EBA which I am taking here is the reference here as our omega t is equal to 0, and because this is our phasor voltages, I took EBA as a reference. So now we are just delaying alpha degree. As I said, it was 0 here, but I delayed here, means your ID is continuing here in the valve 1, and then it is suddenly it is current is sharing from 1 to here 3 during this U period, and then 1 is off and 3 is continue to conduct, and this is your upper voltage and this is a lower voltage here I was talking. This is upper, this is a lower. So I am just starting for this pulse here, this here up to this portion. This is again 60 degree. You can start from here also, then you have to take this portion, then you have to take this portion, then you have to take this remaining portion here, and that is again three different components you are adding. But if you are starting here, so one is here, you can say why I am taking the three components, because the voltages here the different during this period is a different. So here I change from 0 to here alpha plus u, and then alpha plus u here it is again 60 minus u, that is we are getting. We will see more detail about this, even though the graph which I have shown here, this is also very tricky. You can say the current here from 1 it is going to be like this, and 3 is picking like this. It can be, even though you can ask why not it is like this, and why not this is going to be this one. We will see, and we will derive this one also characteristic during this conduction period, how the current is going to change from one valve to another valve, and we will see later on in the same lecture. So now here this is your DC output voltage. As I said, here this we have to write. Already we have our expression for this, we have the expression for this, taking this as a reference. Already in the beginning I wrote, and then if you are going to write here, we can get this expression in here. Means you can say here what we have, which I wrote here. Here I think alpha plus u, here the 60 plus alpha will be there, because we are just delaying for 60 degree we are talking only. Other period we are not talking, because this will continue for the remaining period, but here it is alpha plus 60 degree only we are going, because this is a 60 degree only we are considering, because again it is a symmetric. So here it is alpha to u plus here, and then here up to 60 plus alpha. Now you can say total period here is 60 degree. This upper limit minus the lower limit means 60 degree. So now we are going to just integrate. Now this is, you can see the EC. What was your EC? It was in terms of sine omega t plus pi by 2 it was there. So you can just here you can write here from this EC is equal to, this is the EC is the phase voltage, it is not line to line. So this is a 3 by 2 I have written. This EC, now I have to write EC is nothing but minus EC here I am writing, and minus EC is nothing but your cosine omega t at the same EBA as a reference. Similarly here EBC, here it was a 60 degree lead, here the sine already I have written sine. Here I changed because the EC was in the sine component we wrote, but it was the EC was your omega t plus pi by 2 sine, then it is a minus cosine omega t, and this minus has gone. So this component is appearing here, and this component, and this is the line to line voltage EBC, means it is under root 3 EM. This was your phase voltage, so that's why it was EM here. Simply you integrate it, put the values, you will get this value. So I am not going to integrate and put this value, just you can see that in the steps they are written very well. Here this is a cosine becomes sine integration here. So this is integration alpha to alpha plus u. Here you can say we got this term. Here it is again we are getting, this is a integrated, this is a cosine here, and then we are putting this omega t is equal to alpha plus u, and another it is alpha plus 60, and here you have to simplify, and finally you are getting this value. So here we are getting the final expression. I can write 3 under root 3 EM. EM is the peak value, and it is a 2 pi, and we are getting this cosine alpha plus cosine alpha plus u. Here this is the DC voltage we are getting. This voltage you can see. Now you can find this is this component. It was our VDO. So I can write here it is VDO by 2 here cos alpha plus u. This is the DC output average voltage across this link in case of mode 1, that is your valve 1 and valve 2 and valve 3 are conducting simultaneously. Now here you can see if we put alpha is equal to 0, we are getting the same expression. This alpha is 0 means you are getting the 2 cos alpha 2 will be cancelled, and the Vd is nothing but Vdo cos alpha, which we derived for the ideal case when only 2 valves were conducting. So this is the DC voltage. No doubt maybe this expression may be the complex. There is another way that we can derive it, and in that way here the simply just also, and however I will derive this in the next turn, but you see here from I will see this graph. What we can do, only this area in this complete 60 degree, this area is missing. So what we can do, already we had our from here to here we had without this overlap, we had the 2 valve conductions very well, and then this area can be subtracted. This area is nothing this minus this from this period, and this is simply alpha plus u, and then you can subtract it, you can get again the DC voltage, and we will see on the next lecture. So in this we only derive up to the mode 1 rectification mode on the output voltage, and the next turn again we will derive the current switch over and also this output voltage, and we will see the valve voltages and the DC output voltage per complete cycle in the next lecture. Thank you.